Welcome to Expand Machinery Tip of the Month. I've been getting a few calls about the G76 threading cycle. I'd like to go over some particulars of the threading cycle, G76, G92, G32. So hang on and we'll get started.
Hi, I'm Ken Rule, Senior Applications Engineer for Expand Machinery. Welcome to the Expand Machinery Instruction video series. This video covers single point threading on our Gen Turn line of turning centers. The threading cycles are common between all controls used on the Gen Turn machine line. The first part of this video will cover the mechanics behind doing a single point thread and explain the threading cycles and their use. If you want to go straight to the explanation of the automatic threading cycle G76, please jump to the time listed on the screen. Single point threading is not just a CNC function. It started on manual machines and has been a favorite way to make threads for decades. The manual machines have a lead screw that syncs the carriage movement with the rotation of the spindle. The machinist uses a handle to engage the lead screw to start the tool moving at a lead chosen by the threading gear selected. On the top of the cross slide, there is a smaller slide called a compound slide. This can be rotated so the tool can be advanced at an angle. Machinists found that by rotating the slide and advancing the thread tool at an angle, they could make a cleaner thread and the tool would last longer. The CNC can do this by using the automatic can threading cycle G76. G76 is the most advanced can cycle and is used for threads that are V-shaped. Other threads, like square threads, do not have an angle and can be done using other cycles. The CNC must start the threading tool movement at the same orientation of the spindle for every pass to pick up the lead of the previous pass. There are 3 G codes that will accomplish this: G32, G92, and G76. The simplest CNC threading code is G32. It is identical to G1, except it waits for a marker pulse from the spindle before it starts its move. G32, like G1, moves from point A to point B in a straight line at a given feed rate. The feed rate, inches per revolution, is the lead of the thread, or the reciprocal of the pitch, such as a thread with a 20 thread per inch pitch has a lead of 50 thousandths. The use of G32 has become scarce with the advent of the G92 and G76 can cycles. G32 is only one segment of the threading pass. You still need to program the other 3 segments to complete the threading pass and get ready for the next pass. Before engaging a threading cycle, you must program a start point relative to the thread. I program X about 20 thousandths over the major diameter for OD threads and 20 thousandths under the minor diameter for ID threads. For Z, I like at least 200 thousandths run at the thread to make sure I have passed the imperfect thread length. The imperfect thread length is the distance the Z-axis has to travel during acceleration before reaching the proper speed. During this time, the tool will make a bad thread. The bigger the lead of the thread, the larger the imperfect thread length. Watch that your first thread is not deformed on a high helix threads. The threading pass looks like this: rapid down, wait for a marker pulse and feed in, feed up, and rapid back. This entire pass can be done with one code, G92. We will use a common 1/4-20 thread for our example. The entire pass is a rectangle. By describing the opposite point of the rectangle from the starting point, G92 will complete the rectangle as described. G92 is a modal command in group 1. When you follow the G92 with an X dimension, it will execute another pass at the new X value while using the unchanged Z value for the length of the thread. By programming diminishing X values for an OD thread or increasing values for an ID thread, you can make multiple passes on the thread. Of course, the last X value should be the root diameter of the thread. Using this method, the tool will advance straight into the thread. If you are making a general purpose V thread, then you want to index the tool at a compound angle like they do on a manual lathe. You also want to calculate the X values for constant material removal. As the tool gets deeper in the thread, you want to reduce the amount per pass in X. That's a lot of calculating. So let's allow the control to take care of this for us. After all, it's a computer. We can do this by using G76. The G76 can cycle is a two-line can cycle. The first line sets the parameters of the thread, and the second sets the mechanics on the thread. In the first line, we use the P address to set the number of spring passes, the number of threads that we want to start pulling out of the thread, and the angle of the insert. The P address has 6 digits. You must include a number in each digit as a placeholder. From left to right, the first 2 digits are the number of spring passes, or passes at the root diameter. This is used to take care of any deflection in the part and helps with burrs. The center 2 digits are the number of threads before the end of the thread where the tool starts to chamfer out of the thread. These 2 digits assume a decimal point between them. If you choose to start the end of chamfer at 1.5 threads before the end point, you will use a 1-5 with no decimal point. This is used when the thread has no relief. The last 2 digits are the total included angle of the tool. In the example, we will be making 1 spring pass with a 1.5 thread chamfer at the end and a 60-degree angle. The passes will be calculated at an actual angle of 1/2 a degree less than the right angle of the thread. In this case, 29.5 degrees. The 29.5 degree indexing of the threading tool will cause the leading edge of the insert to bore most of the chip load, and the trailing edge will take a swipe on the back of the V to remove the tool mark from the previous pass. The next address in the first line is Q. As G76 calculates the depth of each pass, the amount gets smaller and smaller as the tool gets deeper into the thread. The passes will mathematically get ridiculously small. The Q in the first line will set the minimum amount the tool will move in X per pass. G76 uses the first pass amount and the root diameter of the thread to determine the amount per pass that X will advance. In this example, we will use Q.002 in the first line. Make this number larger for less passes and smaller for more passes. The last address in the first line is R. The R is the finish allowance, or how much you want to leave for the finish pass. This is the last pass before the spring passes. All the spring passes will be at the same depth after this pass. The second line in the G76 command is where we fill in the mechanics of the thread. The X value is the root diameter of the thread. That's the minor diameter on an OD thread and the major diameter on an ID thread. The control will compare your starting point in X to automatically determine if it is an ID or an OD thread. The Z value is the end of the threading move. If the thread has a relief, you want to program Z well inside the relief. Always set your tool offset to the leading edge of the insert. That way you don't thread into a face. I guarantee the tool point will follow it. The R address in the second line is the taper. The value is the change in the radius of X from the beginning to the end of the entire threading move. For a straight thread, we will use a value of 0 or leave it out. The P address in the second line is the height of the thread. This can be found by subtracting the major diameter of the thread from the minor diameter and divide by 2. The Q address in the second line is the depth of the first pass. This value can be large for soft materials and smaller for harder materials. The F in the second line is the feed rate, or the lead of the thread. In the example, we will be programming a quarter 20 OD thread in aluminum. The resulting G76 should look like this. This code contains the threading information and will create a quarter 20 thread, pulling out 1.5 threads before the end at a compound angle of 29.5 degrees at a minimum depth of 2 thousandths per pass, leaving 2 thousandths for a finish pass to a minor diameter of 188 thousandths and 7/10 at a length of 650 thousandths with no taper, with a single depth of thread of 30 thousandths and 6/10, with the first pass of 15 thousandths at a lead of 50 thousandths per revolution. This concludes the Expand Machinery instruction video on CNC single point threading. Bye for now.